Good afternoon to everyone. My name is Lorena Centarti, and I am a PhD student at the University of Salerno. Today, along with my research group from the Modeling Lab, we will be presenting on the topic Automated Scan-to-BIM methodology for accurate 3D modeling of embedded MEP system. When we talk about building information modeling or BIM, it refers to an intelligent 3D model-based processes that equips architecture, engineering, and construction professionals with tools to plan, design, construct, and manage building more efficiently. Unlike the traditional method, BIM integrates relevant data into a single collaborative environment, not only representing the building's geometry, but also providing information on materials, cost, and maintenance. One of its key applications is MEP, Mechanical, Electrical, and Plumbing System, which are crucial for any building functionality, but can also be challenging to integrate into architectural design. BIM improves visualization and coordination of this system, minimizing potential conflicts during construction. In a building life cycle, BIM MEP, Mechanical, Electrical, and Plumbing is crucial for the design and coordination of technical systems. It focuses on modeling and management MEP to ensure the building functions properly. During the design and construction phases, allow for detailed models where engineers and designers collaborate with architect and structural teams to ensure correct design, coordination, and placement of MEP system. But the question is, when we talk about life cycle path phase for applying BIM MEP in existing building, this process occurs during the operational and maintenance phase of the building. Although the design and construction phases of BIM have already been complete, the implementation of BIM MEP in existing building is primarily used for performance optimization, maintenance planning. So, how make visible what is invisible? Thus, obtaining information will occur through a reverse engineering process, where can we gather data from 2D plans, point clouds, or by scanning the walls. This is always in the context of MEP applications. Once the information has been processed and transferred for a point cloud to a Revit environment, an application programming interface will be created, an API, using various platforms. This will systemize the process of detecting and modeling the system through parameters that geometrically capture features such as thickness, height, position, diameter, and so on. The application of an API, the systematization of modeling, and its precision will enable the operation, maintenance, and renovation of the existing building over time. This will use information from various disciplines or stakeholders involved, facilitating construction management. When working with existing or heritage architecture where accurate information is lacking, the combination of technology for surveying is essential to operate in a BIM environment. As we have seen, the first step is to obtain the information using various surveying techniques available on the market, such as BLK 360 and BLK 2Go, for example, as a laser scanners. The second phase involves making the invisible visible by using various devices to detect pipes or installation within the walls. Although this is a manual phase, it's essential to identify each element and determine the materiality, size, type of system, height, and spatial position. All the presented devices can obtain information for sure, but the chosen one was the device for the application is the Bosch wall detector. It's easy to use, and his ability to detect metal, plastic, wood, and structure, and also electrical system is really great. Once the points cloud has been obtained and the detection of pipe within the walls has been complete, the next step is to create tags for each of the previously detected points using a cyclone field application. That allows 3D data scanned acquired directly in the field to be linked with BLK image laser. The interface also enables the addition of tags, which help to identify the points where pipe pass through, facilitating the definition and tracing of the piping layout. After tagging, we can use Lake Cycle Register 360 to register the point cloud, enhancing the management of the scan data. This software allows us to visualize each scan and the create tags, displaying their names, coordinates, and the associated image. Once the coordinates have been identified, an Excel file is generated to catalog each component, including their position and their coordinates. The third part involves creating an API to be able to automate all this process. An API is a code that determines how a computer program functions and its use to channel information from one part of the software to another one. API allows an application to extract pre-existing files or data within software and use them in another program or within its various levels. This enables semi-automatization for Scan-to-BIM modeling processing for MEP. To create and review API, we use Microsoft Visual Studio as development environment and a program in C#. The first step is to define the input property obtained for the collect data, including coordinates, for example, category types, installation type, material, diameter, and so on. This information is classified and linked according to the function to be executed with the API. Next, we process the data to enable the creation of new elements and modification of the existing components. Finally, after implementing those processes, we generate the in-place 3D element within Revit, resulting in a 3D MEP model that reflects all the defined characteristics. So this is the flowchart illustrates our methodology, which is clearly divided into 3 stages, with the third being the creation of the Revit API. This flowchart illustrates the foundation for the API development and all the process that begins with selected type of pipe and finish with the creation of the different pipes. Here we can see in 3 different videos. The first application case, it was in a boiler room where a 3D digital model was obtained through the creation of a point cloud, allowing us to reproduce the space and establish the basis for modeling the facility on site. Our wall detector was used to identify no visible pipes within the wall. Through this detector, the point corresponding to the path and location of the pipes were marked and then converted into real tags using the Cyclone Field 360 application. Once the coordinates of the points were obtained, they were exported to the Create platform, facilitating the systematization of the processes and the creation of the pipe route. The application case in the boiler room was a straightforward process that allowed us to apply each stage of our methodology and test the established procedure. It was crucial to be very careful, for example, when using the reference system of the point cloud into relation with each other with the tags and the coordinates obtained during the transfer of this information to the API. When working in a BIM environment, we understand that modeling MEP system is done using linking models. So it was necessary also to establish this as a key parameter of the API. We also assigned a specific name to each tag. So so we can create a fitting, simple, but the system becomes more complex with additional fittings. That's why we require a clear naming code to avoid any confusion to the API. The Create API is functional for piping system, both rigid and flexible. Each characteristic of the installation is directly extracted from Revit, allowing the API to read the classification. So we use the same names, the same code, and the same, for example, families. This ensures that the API not only automates the creation and modification of components, but also maintains the coherence with existing build models. To demonstrate the real-world application of the API and explore future possibilities is more complex in scenario, we conducted a survey of the Church of San Dominic in Salerno. We performed the site survey using a scanner to generate a point cloud in E57 format. Following the previously mentioned data collecting methodology, we create a 3D model of the church and its installation using the point cloud as a basis for reconstructing the 3D model in Revit. This model also serves as a target area.
Lorena, sorry for interrupting you. You have 2 minutes, 1 minute to conclude. Thank you.
Almost finished. Okay. So I was saying, we create a model, we do it in Revit, and then we use this model as a target area for our extended reality application, which we developed using the Euphoria area target generator. Once the 3D model was built in Revit, we exported to PFX format using 3D maps, and then importing into Unity. In Unity, we utilized the Euphoria engineering package to develop our X3 application, employing C# as the programming language. The objective was to use the area target generated from the point cloud and 3D model to highlight points of interest or argument reality. Finally, the application can be compiled for multiple platforms. In our case, we will use Android and ISO for testing. And this is the video and the image where we can see how we use this model. And then we use Unity as an area target, and then detect and visualize in X-rays. In conclusion, the automation of MEP system design is an existing built-in driven by a combination of laser scanner, sensor, and Google. As an API development offer a transformative approach. By integrating reverse engineering techniques, the solution not only automates and optimizes MEP redesigned, but also provides output that can be visualized in models, plans, X-ray, platform, and Google. The success of this process relies on a strong interdisciplinary collaboration, merging expertise from engineering, architecture, software development, and X-ray technology to create a seamless and efficient solution for retrofitting buildings.
Thank you, Lorena. Really
Thank you
interesting.
so much.